So this involves a conductor, a metal, a neutral conductor. So it's a conductor with a hollow cavity. So here's the conductor. There is no, I would assume it's a sphere. There is nothing special about the sphere. And then there is a cavity here. So this is the cavity, okay? So it's neutral. Nothing is going on. So please focus with me. So this is the conductor, right? What's inside here?
100.
So initially it's empty, right?
Yeah.
And the conductor is neutral.
Yes.
Okay. So there is nothing.
Yes.
Then somebody is going to reach in, going to come in and place some charge here, right? Some negative charge that's off. Oh, yeah. Okay. So somebody put inside that cavity 100 nanocoulombs. So someone comes here and places 100, some charge here, positive 100 nanocoulombs, okay? 100 nanocoulombs in there. This 100 nanocoulombs is just floating in the cavity somehow. Somebody suspended it there. So it's not going to drop and hit the conductor. It's just float. And then what they're going to also do, they're going to, let's say, they rub their feet against the ground, they get charged up, and then touch the conductor. Okay. So they touch the conductor and they place an additional, this charge now is negative 50 nanocoulombs on the conductor.
So I have a question before that happens.
Yes.
Like, say those happened in order,
Yeah.
and right now we just have the 100 nanocoulombs
Okay.
in there.
We're going to do it in steps. Yeah, go ahead.
What would happen at that point?
Good.
Would there be a negative 100 around it that cancels out that electric field, and then another, I guess, positive 100 on the surface of the?
That's right. So what would happen now? Let's say before we add charge to the conductor is neutral. We put charge here. The conductor is still neutral. Still has net charge of 0, right? So this positive charge, let's emphasize and put plus. Okay. It will attract some minuses. It will attract some minus charges, negatives here. And then when it attracts negatives, it will leave off net positives out there, right? It will leave net positives out here. Okay.
And those are outside of the conductor?
They're on the outer surface, yeah.
Okay.
And these are on the inner surface.
Okay.
So now, exactly how much negative does it attract? Right? Exactly how much negative does it attract? And the answer is, it will attract a negative 100 nanocoulombs. And we said the reason is, you use Gauss's law. So you say, draw a Gaussian surface. Draw a Gaussian surface. I don't want dashed lines because they look like negatives. Draw a Gaussian surface. And you know E dot dA is equal to Q enclosed over epsilon naught. What's the electric field out here? 0, because it's a conductor. Inside the conductor, the electric field is 0. So everywhere on this surface, the electric field is 0. So E dot dA ends up being 0. Left side is 0. So Q enclosed over epsilon naught is 0. It means Q enclosed is 0. We know we're enclosed in 100 nanocoulombs. So we must be enclosed in here an additional negative 100 so that the total would be 0. So it will attract negative 100. So now let's see, leaving off positive 100 out here, right?
Mm-hmm.
Yeah. Next, we're going to touch our sphere and add to it negative 50, right? Yeah. So this is the positive 100. we touched our conductor now, and we placed negative 50 nanocoulombs. So the conductor now has how much net charge? What's the net charge on the conductor when you touch it, then you place negative 50? It would be negative 50, yeah. You added negative 50, so it will have negative 50 total. Now, you adding negative 50 nanocoulombs, will it change the fact that the attracted charge is still negative 100 or no? It will not, because the electric field is still zero inside the conductor, right? And therefore, the charge enclosed in the Gaussian surface is still zero. Yes, the charge enclosed is still zero, but therefore this here will still be minus 100. So yeah, you will still have minus 100. So minus 100. So how much do we have here on the outer surface? Remember, the net charge is negative 50, right? So what must we have here?
Negative 150, or I guess just
Negative
50.
50.
Just
Just
50.
50.
Just 50.
Just 50, because positive 50 plus negative 100 is negative 50. So yeah, it's going to be a positive. So positive 50. Was that the question?
I guess I was confused about how the charges on the outside interact with the charges on the inside, and like if they create electric fields or not.
They don't.
Yeah.
The electric field must be zero inside the conductor.
And so do all like the charges on the outside just project right
Yes.
outward?
Yeah,
They don't, nothing goes inside?
They will in fact distribute themselves. Yeah, spherically symmetric, yeah.
Okay.
Because these two, they basically cancel one another and they do not affect the outside.
So like the negatives would project inwards and the positive 100 would project outwards, so those cancel each other?
Yeah, they do.
And then just the ones on the outside, they wouldn't push. I guess when I originally thought about it, it seemed like there would be electric field going inside and that would mess up the, I guess the problem, and it didn't make sense.
Sorry, the problem what you say was gonna be for the 50? The 50, was that from the problem?
Yeah.
Okay.
Separate from this, just a velocity question.
A velocity.
Velocity, if you have a force exert on, you have two particles,
Yeah.
two particles.
Yeah.
The force exert from one to another, and you're finding a velocity, we had a question at the end of that. Remember how we have like, we did an example in class where we had the two charged sheets or plates or whatever, and we had that particle going through.
That was conservation of energy. Oh, I see, yeah.
Remember that velocity, if we were to have, let's just say, I'm not sure if this is relevant to what we're gonna be doing, but if we had, you know, a charge here, another charge here, we're trying to find the total velocity of this particle, you know, in this field, electric field. Are we doing anything like that? I feel like we did something like that, but I don't remember if we.
We did, I remember now what you were saying.
There's like some sort of theta and there was.
Yeah.
Can we apply, you know, the force equals the negative?
Newton's laws, yeah.
Sorry,
Newton's laws.
Newton's laws, can we do force equals the negative gradient vector of potential, electric potential?
No,
We're not
because,
doing that?
this exam only covers Gauss's law. And,
Right, okay.
nobody-
Could we use that though to find the velocity?
We're not allowed to because,
Not allowed to do this, okay, so we have to have, okay.
we didn't cover that. This exam doesn't cover that.
Oh, yeah, it's plus 50 nanocoulombs. Is that like the original charge of a conductor?
Negative 50 was the original.
Negative 50 was the net
It's
charge.
not much of a- negative 50. Yeah, it does.
Okay, that makes sense.